speaker is Mahtab Ahmed, who will be telling us about attention in trees.
Hello everyone. My name is Mahtab. I'm going to present our paper titled You Only Need Attention to Traverse Trees. I'm a PhD student in Department of Computer Science at Western, a postgraduate affiliate at Vector Institute, and an AI intern on Message Point. This project is funded by MyTex and INSERC. So in recent NLP research, a topic of interest is to find good sentence representation to solve any kind of downstream tasks. The standard sequential based models like LSTMs and the attention models actually overlooks the tree information, the grammatical information that coexist in the text. So in this paper, we actually propose a tree-based transformer where you can traverse the dependency trees and the constituency trees. When you traverse the dependency tree, you formulate the word-level dependency. When you traverse the constituency tree, you formulate the phrase-level syntaxes. So we know that there exists RNN, which works on the sequential data. Then there's a recursive version, which is called recursive RNN, which works on the tree structure data. You have LSTM, which works on sequential data. Then you have tree LSTM, which works on the tree structure data. You have transformer, which works on the sequential data. But so in this study, we try to propose tree transformer, but the task would be different. It's not going to be the machine translation task, but it works on any kind of trees, like dependency of the constituency trees. The design of tree transformer. So ever since you design a model, you start with how you're going to represent data. So when you have a tree, when you try to say traverse a subtree, you are going to represent, in terms of dependency tree, you are going to represent each of the subtree by the vector representation of the parent of that subtree and all the children. So XD is the vector representation of all the parents and the children. When you traverse the constituency tree, we know that in the constituency tree we have words only at the leaf nodes. You don't have anything inside it. So everything is the phrase level version. So for the constituency tree, a node, a subtree would be represented by the vector representation of all the children. So once you have this vector representation of this, once you have this representation of the node, then we are going to find a function called f, which is going to give the attentive transform representation of this whole subtree. So as a function, as this f, we try to explore the multi-head attention block and the multi-branch attention block. However, the multi-branch attention block actually works better when we did the experiment. So on this note, so how this multi-branch attention actually works. So you starts with the standard dot product attention where you have the QK transpose times V and a softmax over this QK transpose. So this QK and V are going to be the same for a subtree because so we hypothesize that when you have a subtree, the tree is going to attend itself with respect to itself. But we are not restricted to the just one, that means the single head attention. We are looking at the multi-branch attention. So we were dealing with n branches. So we created n different tensors, and we replicate the n different tensors for the representation of that tree, and then we have n different parameters for each of these tensors. So we apply these attention blocks. So after applying this attention block, we have this n different branch representation for each of this subtree. Then once we have this branch representation, we did a linear transformation of that branch, and then we apply a residual connection followed by a layer normalization block. Once you have this representation, so each of the branch actually tells something in terms of semantic representation of that tree. So we further scale with another parameter kappa. This kappa is going to be a probability in terms of how many branches you have. Once you have this representation, we actually further retransform it using a position-wise convolution neural network where two convolution nets are going on back-to-back with a Rayleigh activation in between. And then we further do a linear weighted summation over this branch representation. So all the branches are squashed into one branch. Once you have this one branch representation, and you have the original branch representation in terms of the word vectors, so you do another residual connection followed by a nonlinear transformation with tan h being the nonlinear activation function. Once you have this representation, you have multiple vectors in terms of a tree or a subtree. Then you do a summation, linear summation, which is the element-wise summation. You end up with just one vector. And so you do it recursively for every subtree, and once you reach the node, you get the entire representation of the tree. So this is how the model looks like. So when you traverse this portion of the tree, so the traversal is going to look like this. When you traverse this portion of the tree, the traverse is going to look like this, and when you traverse the final root node, the traversal is going to look like this. And the attention block is the one in the middle. So this gives you one vector representation of the entire tree. For the experiment, we did 4 tasks. One is the sentiment analysis on the Stanford sentiment tree bank. The second one is the semantic relatedness task from the SIG dataset. The third one is the natural language inference task from the SIG dataset. And the fourth one is the paraphrase identification task on the MSRP dataset. So the first dataset was available in the tree form, but the last two was we used Stanford sentiment, Stanford's dependency parser and the constituency parser to get the parse trees. These are the hyperparameters. So the dimension of the query key and the value was set to 50. We used 6 parallel heads, 6 position-wise convolution neural network layers, 6 branches. The dropout was set to 0.1. And each of the position-wise convolution neural network layers were composed of 2 convolutions. So the first convolution uses 341 kernels of size 1 times 1, and the second one uses 300 1 times 1 kernels. So these are the results. So if you look at the performance of this tree transformer, the performance is quite close to the one with the dependency tree and the constituency tree LSTMs, but it's much better than the dependency tree RN, which uses just one linear transformation as the composition function. So attention is much better choice as a composition function. You look at this result, it is quite close to the one we are getting with the tree LSTMs. You look at this one, quite close to the one we are getting with all the tree LSTMs and the dependency tree RNA networks. And the fourth one is quite close to the LSTMs and is better than the dependency tree RNAs. And in all the 3 cases, these 3 cases, the tree-based transformer is much better than if you use just encoder portion of the transformer. That means the grammatical information is giving something to the model, at least. We did one ablation study, a few ablation studies actually. The first one is, we know that in transformer, the positional encoding is a vital factor, because if you want to mimic the behavior of the LSTM with the transformer, you want to know that which word comes first and which word comes second, so on. But for the trees, our intuition was that in trees, the position informations are inherently encoded, because when you look at a word, you're looking at the word based on the position in terms of the grammars. So when we did the experiment, so our intuition was right. When you use positional encoding, every time the performance gets worse. So you can see in all the cases, the performance are much worse if you use the positional information in the trees. The last one, the second ablation study that we did was we wanted to look which attention module works well as a composition function. So we experimented with the single head attention, multi-head attention block, and the multi-branch attention block. So you can see the result for the first, in this task, the single head attention actually wins, but for the other tasks, multi-branch attention works comparatively better other than all the attention block as the composition function. So we can say that multi-branch attention is a good choice for the composition function as it for the trees. So this is one of the sample results from the Stanford sentiment tree bank dataset. So you can see that in all the cases, so there are 3 words tagged as positive: the word will, us, and sincere. Us is tagged as positive. It's weird, but still, every time we see this word, our model actually giving high probability to the branches where this word actually occurs, and all these 3 words actually occurred in the right side of the tree with respect to the root node. So you can see our model is also giving positive sentiment on the right side of the tree, and the overall sentiment is also positive. So it's actually doing correct in this case. So in this paper, we actually proposed a tree-based transformer which can successfully encode the natural language grammar trees utilizing the modules designed for the standard transformer. And you can also use the attention module as a composition function with the grammatical information rather than just bag of words. So you can actually formulate the grammars. And the performance we achieved was on par with the tree LSTMs, and it's better than the transformer-based encoders. Thanks.
right, we have time for a couple of quick questions. I have a quick one. So in these tree models, so basically you have in the branching attention mechanism, you have something that knows what child of, what daughter node of a particular non-terminal is being put together. So you're getting sort of we're getting a position-dependent representation, but it seems like the label of the non-terminal is going to be extremely important for determining sort of how that composes. So the way a preposition composes with its argument is different than the way a verb composes. Did you look at possibly making that those parameters that parameterize the branch attention look at the non-terminal that's being joined?
Thanks for the question. So we haven't looked at the labels in the tree. That means the preposition or the phrases. But every time if your node is labeled with a sentiment, so every time a loss function is going on to minimize that the sentimental loss, right? So we haven't looked at the labels, but the data set is tagged as you have words, you have labels on each of the nodes. So we use different loss functions on each of these nodes, and then finally combine and then minimize that loss.
Right. I guess this is more of a general question, and sort of if you weren't doing, say, the Sentinel one where you had like supervision at every position, it would be potentially one. Here you go.
Giuseppe Caranini from UBC. So I was wondering why you have the number of branches as an hyperparameter.
The number of branches?
Yes.
It actually you can. So it depends on how you're dealing with the word vectors. So if your word vector is 300-dimensional vector, and if your query key and value matrices are set to 50-dimensional, then there's no choice. You have to make it 6 in order to say concatenate them to 300. So it depends on which word vector you use. So if you use just 50-dimensional word vector, so the number of branches would be just 1.
All right, let's thank our speaker.